The dinosaurs didn't die badly. Honestly, getting wiped out by a single asteroid in a matter of days might be the most merciful exit in the 4 billion-year history of life on this planet. Because before that rock ever showed up, Earth had already run 4 mass extinctions, and the weapons it used were so bizarre, so completely unhinged, that an asteroid almost feels like a kindness by comparison. One of those extinctions was triggered by an invisible beam of cosmic energy traveling at the speed of light. Another one, and I'm not joking, was caused by trees. The first trees. The trees that were supposed to make everything better. In a few minutes, you're going to understand exactly why the age of the dinosaurs wasn't the dark chapter of Earth's story. It was the easy part. Let's start with the trees, because this one will genuinely rewire something in your brain. Every school, every nature documentary, every reforestation campaign on the planet sends the same message. Trees are good. Trees are life. Trees are the solution. And in fairness, on a living, functioning planet with a working ecosystem, that's completely true. But wind the clock back about 375 million years to a period called the Devonian, and you land in a world where trees had just evolved for the first time. And they were, without any exaggeration, one of the most catastrophically destructive forces this planet had ever seen. The specific culprit was a plant called Archaeopteris, sometimes called the ancient fern tree. Before it showed up, Earth's landmasses were basically vast stretches of bare rock and low-lying moss. There was no deep soil. There were no root systems drilling down into the earth. The land was geologically stable in a way it hadn't been in a long time. Then Archaeopteris appeared, spread across the continents, and started doing what trees do, growing roots. Except these weren't gentle roots feeling their way through soft dirt. These were the first serious root systems in the history of the planet, and they had nowhere to go but into solid rock. So that's what they did. They evolved to secrete acidic compounds, boring into hard stone, slowly dissolving it, grinding it into something that would eventually become soil. For the tree, this was just survival. For the planet, it was the beginning of a disaster. When you grind up ancient rock, you release what's been locked inside it for hundreds of millions of years. Phosphorus, calcium, iron, the same nutrients that every living thing needs to grow. And once those nutrients were loose in the soil, the rains did what rain always does. It washed everything downhill, into rivers. And from rivers, into the ocean. Now here's where it goes from interesting geology to global catastrophe. The ocean had never seen a nutrient dump at this scale before. The result was something called eutrophication. And if you've ever seen a pond turn completely green in summer, that thick, slimy blanket of algae covering the surface, you already have a rough idea of what happened. Except picture that, but covering entire ocean coastlines. Algae bloomed in massive quantities, fueled by all that incoming phosphorus and nitrogen, carpeting the sea surface so densely that sunlight couldn't penetrate below. And when algae blooms, it eventually dies. And eventually dies. All of it, at once, in enormous quantities. That's when things get truly dark. All those dead algae cells sank and started decomposing. Decomposition needs bacteria. And bacteria are very good at their job. So good. In fact, that they consumed essentially all of the dissolved oxygen in the water around them. The scientific term for this is an anoxic event. The practical term is the ocean suffocated. And in this suffocating, algae-choked, oxygen-stripped ocean lived Dunkleosteus. If you've never looked up Dunkleosteus, do it after this. It was one of the most terrifying animals in the history of life. A heavily armored, predatory fish that could grow to roughly the size of a city bus, with a bone-crushing jaw that could open and slam shut in a fraction of a second. It had no natural predators. It was the apex of the Devonian Ocean. In any fair contest, Dunkleosteus was unbeatable. Oxygen deprivation is not a fair contest. Picture this animal, this absolute monster of the prehistoric seas, slowly suffocating in a thick green soup, its gills pumping uselessly against water that had no oxygen left to give. It didn't matter how big it was. It didn't matter how strong its jaws were. You can't bite your way out of a dead ocean. The fish that survived in normal times by hiding in the bottom mud were also done. Even the ones that had evolved bone plates thick enough to stop a predator. Even the ones that could occasionally gasp air from shallow water. When the entire coastal ecosystem collapses, when the shore itself becomes a stagnant, oxygen-free swamp, there's no shallow water left to retreat to. There's nowhere to go. The Devonian extinction killed off roughly 75% of all species on Earth. 3 out of every 4 species wiped out over a few million years because trees learned to dig roots. Land life, without even noticing, slowly poisoned the ocean to death. The whole thing took hundreds of thousands of years to fully play out. Slow, chemical, inexorable. But Earth doesn't always work slowly. For a truly fast kill, you have to go back even further, about 445 million years, to the Ordovician period, and look not at something happening on Earth, but at something that happened in deep space, aimed at Earth, with no warning at all. Here's what the planet actually looked like at this point. And this detail always gets me. Earth had rings, actual rings. Like Saturn, around the equator, there was a broad band of orbiting rock debris, glittering in the sunlight, visible from the surface. It was the result of a large asteroid that had been pulled in by Earth's gravity and crossed what physicists call the Roche limit, the distance at which a planet's gravitational pull is strong enough to tear a smaller body apart rather than just capture it. The tidal forces, the difference between how hard Earth's gravity pulled on the near side of the asteroid versus the far side, physically ripped the rock apart. Instead of one impact, Earth got trillions of fragments spreading out into an orbital ring, and that ring was constantly raining debris down onto the surface. The early Ordovician was geologically violent in a way that's hard to fully picture. Then the gamma ray burst hit. Somewhere in the deep universe, far from Earth, a massive star died. Not a regular stellar death, a catastrophic collapse into a black hole, releasing a burst of gamma radiation in a focused beam across space. These events are among the most energetic things that happen anywhere in the observable universe. And this one was pointed, even if only by random chance, roughly at Earth. The burst lasted about 10 seconds. 10 seconds of high-energy radiation moving at the speed of light across the cosmos. And then it arrived here. 10 seconds is nothing. 10 seconds is the length of time it takes to tie your shoes. But 10 seconds of a gamma-ray burst is enough to strip away the ozone layer. And not just damage it, half the ozone layer, gone in under a minute. The protective shield that filters out ultraviolet radiation from the sun, the one that makes complex surface life possible at all, was suddenly half as thick as it had been. Ultraviolet light began hammering the planet's surface and ocean at double the intensity. Photosynthetic plankton, the base of the entire marine food web, the organisms responsible for producing a huge percentage of Earth's oxygen, began dying. When the base of the food chain collapses, everything built on top of it collapses too, one level at a time. And then, as if the universe felt it hadn't made its point clearly enough, the ring system made things worse. The same debris field that had formed after the Roche limit event continued to block sunlight reaching the equatorial regions. Global temperatures began to drop. Ice sheets expanded from the poles. Sea levels fell. The oceans that had covered most of the continents began to retreat, and the shallow coastal environments, the exact environments where the most diverse marine life lived, dried up or froze over. The Ordovician extinction killed off roughly 85% of all marine species. A 1-2 punch of cosmic radiation and ice age, delivered from the other side of the universe. But even that, even a gamma ray burst and a ring system and a global ice age wasn't the worst of it. The worst of it was the Permian. The Permian Triassic extinction event, which happened about 252 million years ago, is called the Great Dying by paleontologists. And that name is not an exaggeration. This is the event that killed 96% of all marine species and 70% of all land vertebrates. Not a majority. Not most. 96% of everything living in the ocean. Dead! And the way it happened is so relentlessly horrifying that when you actually understand the mechanism, you start to see why every extinction before and after it looks mild by comparison. It started in what is now Siberia. But this wasn't ordinary volcanic activity. What geologists called the Siberian Traps was a volcanic eruption event unlike anything that's happened in the last several hundred million years. An area roughly the size of half of Europe, where the crust fractured open and became a sea of boiling, erupting magma. It didn't last days or years. It burned, continuously, for hundreds of thousands of years. The volume of toxic gases and carbon dioxide pumped into the atmosphere during this period is almost incomprehensible. Carbon dioxide in huge quantities acts as an insulating blanket around the planet. More CO2 means more heat trapped near the surface. Global temperatures began to climb. For land animals, this meant heat, drought, and air increasingly laced with sulfur dioxide and other toxic gases from the eruptions. Bad enough on its own, but for the ocean, it was even more direct. Warmer air means warmer water, and as ocean temperatures rose into the high tropics, some estimates put tropical sea surface temperatures above 40 degrees Celsius. The chemistry of the water changed in ways that nothing alive was prepared for. Proteins begin to denature above certain temperatures. Oxygen dissolves less efficiently in warm water. The ocean was, in a very real sense, starting to cook. In this overheated, oxygen-depleted ocean, something happened that turned a bad extinction into an almost total one. Anaerobic bacteria, the kind that thrive in environments without oxygen, proliferated across the deep ocean floor. And the waste product they produce when they metabolize is hydrogen sulfide, a gas that is toxic to most complex life, even in tiny concentrations. In large quantities, it's lethal in seconds. Hydrogen sulfide has a characteristic smell, the same sharp, rotten egg odor that indicates a dangerously unsafe environment. The oceans of the late Permian were producing this gas in vast quantities. It bubbled up through the water column, broke the surface, and entered the atmosphere in concentrations that turned the air itself into a slow poison. The dominant land predators of this period were powerful, fast-moving reptiles, some of them carrying huge saber-like canine teeth, apex hunters who had dominated their ecosystems for millions of years. None of that mattered when the air turned bad. Poison doesn't respect speed or size or weaponry. These animals died in acidic rain, in sulfurous air, their systems shutting down from a threat they had no evolutionary adaptation to handle. The Great Dying is the only mass extinction in Earth's history where even the insects, which have survived essentially every other catastrophe this planet has thrown at life, took significant losses. When insects start dying, you know the situation is genuinely extreme. Earth had reduced itself to a near-sterile rock, kept alive only by the hardiest burrowing organisms that could find clean air or water somewhere underground. One extinction. 96%. So when you come back to the question of how the dinosaurs emerged, the answer isn't they were tough, or they were big, or they were smart. The honest answer is that they had the right hardware for a poisoned world. The extinction at the end of the Triassic, around 200 million years ago, was triggered by more volcanic activity related to the breakup of the supercontinent Pangaea. This time, the warming ocean destabilized something on the seafloor that scientists describe under a hypothesis called the methane hydrate gun. At extreme depth and extremely cold temperatures, methane gas can be locked into a kind of solid ice structure, stable as long as the conditions stay cold. When submarine volcanic activity warmed the deep water past a tipping point, These ice structures broke down and released their methane directly into the water column and then into the atmosphere. Methane is a greenhouse gas roughly 30 times more potent than carbon dioxide by weight. The climate lurched. Global temperatures spiked again. The air got thin, hot, and toxic. The animals that ruled the Triassic were large, crocodile-like reptiles, some of them weighing close to 2 tons, designed for a more temperate, oxygen-rich world. When the air quality collapsed, their respiratory systems couldn't cope. They died in large numbers. Their ecological niches opened up, and the dinosaurs, who had existed as relatively small, marginal animals during much of the Triassic, suddenly found themselves inheriting an almost empty planet. Why did they survive when the bigger, better established animals didn't? The answer is their lungs, or more precisely, their air sac system. Human lungs work like bellows. Inhale, they expand. Exhale, they compress. At the end of every exhale, some stale air is still left in the system. The dead space in the bronchial tubes, the residual volume in the alveoli. This means that with every breath you take, you're never actually getting 100% fresh air. You're always diluting the new oxygen with leftover carbon dioxide in a well-oxygenated environment. This is fine. In thin, low oxygen, potentially toxic air, this is a serious limitation. Dinosaurs had a completely different system. In addition to their lungs, they had a network of internal air sacs that connected to bones throughout the skeleton. You can actually see the evidence of this in dinosaur fossils, in the hollow, pneumatized bones that have puzzled scientists for decades. This system created a unidirectional flow of air. Instead of air going in, bouncing around, and coming back out the same way, it flowed in a single continuous loop through the lungs. Every breath delivered entirely fresh air to the gas exchange surfaces. There was no mixing with residual air, no dead space, no dilution. Even in an oxygen-poor, high-altitude, or partially toxic atmosphere, a dinosaur could extract oxygen with remarkable efficiency. This is the same basic system that birds use today, because birds are, in the most literal evolutionary sense, avian dinosaurs. It's one reason birds can fly at altitudes where a mammal would lose consciousness. And it's the reason that during the Triassic-Jurassic extinction, when the competition died of respiratory failure, the dinosaurs didn't even slow down. The Great Dying had cleared the board. The end-Triassic extinction cleared the board again, and every time the board cleared, the survivors were the ones with a specific advantage that matched the specific hell they had to survive. Dinosaurs didn't conquer the world by being the strongest. They won because they could breathe when nothing else could. They ruled for about 135 million years. A stretch of time so long that the entire history of our species is essentially a rounding error in comparison. Until the sky lit up. 66 million years ago. A rock approximately 10 kilometers across hit the Yucatan Peninsula at tens of thousands of kilometers per hour. The energy released was equivalent to billions of nuclear weapons detonating simultaneously. The impact vaporized rock and seawater, blasted debris into the upper atmosphere, triggered massive wildfires across entire continents, and then blanketed the planet in a years-long cloud of soot and particulate matter that blocked the sun and caused a global winter. The food chains collapsed. Without sunlight, photosynthesis stopped. Without photosynthesis, herbivores starved. Without herbivores, the predators that fed on them died. The non-avian dinosaurs, with all their respiratory advantages, with all their evolutionary refinements, with 135 million years of successful adaptation behind them, were gone in geological eye blink. A few thousand years at most. Here's what I keep coming back to. Though, after everything you just heard, the trees acidifying the ocean over hundreds of thousands of years, the 10-second gamma ray burst from across the universe, the 250 million-year-old poison event that killed 96% of everything in the sea, the asteroid feels different now, doesn't it? Compared to slowly suffocating in a green anoxic soup that used to be an ocean? Compared to having your DNA torn apart by ultraviolet radiation while an ice age closes in? Compared to being a 2-ton apex predator dying in sulfur-laced acid rain while the air turns to poison around you? A rock from space is, by the standards of Earth's history, one of the cleaner endings. Fast. Decisive. No drawn-out suffering. The asteroid, in a genuinely strange way, was almost merciful. Earth has reset itself at least 5 times that we know of. It has used every tool available to it. Invisible radiation from a dead star light years away, nutrients from the first trees, its own tectonic machinery boiling poisons out of the deep crust, frozen methane bombs buried on the ocean floor. Every single time, the creatures that seemed most dominant, the ones with the biggest teeth, the thickest armor, the longest reign, went down. And every single time, the survivors weren't the strongest. They were the ones with the right weird adaptation for that specific hell. The dinosaurs breathed their way to dominance. Whatever comes next will have its own answer. We're 66 million years removed from the last reset. The geological record suggests these events aren't random flukes. They're patterns, driven by the deep mechanics of a living, active planet. Tectonic plates are still moving. The ocean floor still holds its frozen methane. Massive stars are still collapsing somewhere in the universe. The question of whether Earth is currently stable or just quiet is one that geologists genuinely argue about. The evidence for a 6th mass extinction is not science fiction. It shows up in biodiversity loss data, in ocean chemistry, in the rate at which species are disappearing. If there is a 6th extinction, what's the survival trick? What's the equivalent of the air sac system, the weird, seemingly minor adaptation that looks useless until the world ends and suddenly it's the only thing that matters? What kind of hell will it be designed to handle? I genuinely don't know. But I think about the dinosaurs. I think about how they spent the Triassic as minor players, outcompeted by bigger animals, seemingly unremarkable. And then the air changed, and it turned out they'd been carrying the right equipment all along. History doesn't repeat exactly, but this planet has a pattern, and the pattern is this. Everything that looks permanent is temporary, and the thing that inherits the future usually isn't the thing you'd bet on. Drop your theory about what survives the next one in the comments. I'm genuinely curious what you think the edge case looks like this time.